Ever gazed upon a colossal ship and wondered how such a mammoth structure floats on water? Well, it's not magic, but science. The answer lies in the principle of buoyancy, a concept that has puzzled thinkers for centuries. But why does buoyancy matter? Why don't these massive giants sink to the bottom of the ocean? This fascinating conundrum is not as complex as it seems. Hold on to your hats because we're about to dive deep into the science of buoyancy. First things first, what exactly is buoyancy? Well, buoyancy is a fascinating concept that quite literally keeps us afloat. It's the upward force exerted by a fluid, such as water, that opposes the weight of an immersed object. In a nutshell, buoyancy is the reason why things float. Now let's take a step back in time. The principle of buoyancy was first discovered by an ancient Greek scientist named Archimedes. While taking a bath, he noticed that the water level rose as he got in, and this sparked a brilliant revelation. This led him to formulate Archimedes' principle, which states that the upward buoyant force exerted on a body immersed in a fluid is equal to the weight of the fluid that the body displaces. In simpler terms, if you throw a stone into a pond, the water level rises. That rise is directly proportional to the volume of the stone. The weight of that displaced water is then exerted as an upward force on the stone. But let's pause for a moment. If this principle holds true, then how do heavy objects like ships, which clearly weigh more than the water they displace, manage to stay afloat? So the key to floating is all about displacing water. But how does this apply to our massive ships? Stay tuned as we delve deeper into the design and structure of ships, and how they use the principle of buoyancy to their advantage. Let's set sail into the world of ship design. It's not just about creating a vessel that looks good, it's about engineering a structure that can float. The design and shape of a ship play a crucial role in displacing a large volume of water, thereby ensuring the ship stays afloat. The hull, that's the body of the ship, is carefully crafted to be streamlined. This shape allows the ship to move through the water more efficiently and displace a significant amount of water. The hull's design also distributes the ship's weight evenly across a large surface area, which helps to increase buoyancy. Remember, a ship floats not because it's light, but because it's able to displace water equal to its own weight. Think of it as a game of balance between the weight of the ship and the water it displaces. So, ship design is all about displacing enough water. But what about the weight of the ship itself? It's all about balance, not just in life, but also in ships. You see, a ship's stability and buoyancy are largely determined by how its weight is distributed. If a ship's weight is unevenly distributed, it can tilt, or even capsize. But don't worry, shipbuilders have a few tricks up their sleeves to prevent such catastrophes. One of these tricks is the use of ballast tanks. These are large compartments within the ship where water can be pumped in or out. When a ship needs to stabilize, it can fill these tanks to increase its weight and lower its center of gravity. Conversely, when the ship needs to lighten up, it can simply pump the water out. Cargo placement is another strategic maneuver. The cargo is arranged in a way that evenly distributes the weight across the ship, ensuring equilibrium. So weight distribution is a balancing act. But what about the materials ships are made of? Ever wondered what materials make up these floating giants? To achieve buoyancy, ships use lightweight materials in their construction. Steel, despite its weight, is a popular choice due to its strength and durability. It's shaped into thin sheets and structured to form a hull that displaces a significant volume of water, contributing to buoyancy. Aluminum, another common material, offers the advantage of being lighter than steel, further enhancing buoyancy. But it doesn't stop there. Modern shipbuilding has embraced innovative materials like fiberglass and composite materials. These materials are not just lightweight, but also highly resistant to corrosion, increasing a ship's lifespan. Let's not forget the role of air. The ship's hollow structure creates large air-filled spaces, reducing the overall density of the ship, making it less dense than the water it displaces. So the right materials give ships their floating prowess. But there's one more key player: water itself. Water everywhere, helping ships not to sink. Now, let's dive into the role of displacement and density in keeping these maritime marvels afloat. Ships essentially work by displacing their weight in water. This displacement creates an upward force, or buoyancy, that counteracts the ship's weight. But here's the key: the ship needs to have a lower overall density than the fluid it's in. Density, in this context, is the mass of the ship divided by the volume of water displaced. Even though ships are made of materials denser than water, like steel, their hollow design means they displace a large volume of water, resulting in a lower average density. And did you know, the density of the water itself plays a role too? Salt water is denser than fresh water, meaning it provides more buoyancy. That's why a ship can carry more cargo in the ocean than in a river. So, it's not just about the ship, but also the water it sails on. So, why do massive ships float? It's a fascinating interplay of science and engineering. We've learned that buoyancy, the very principle that keeps objects afloat, is key. It's the upward force equal to the weight of the fluid displaced by an object, a principle discovered by none other than the ancient Greek scientist Archimedes. But that's just the tip of the iceberg. The design and shape of ships, particularly their streamlined hulls, play a crucial role in displacing a large volume of water, thus allowing these giants to stay afloat. Equally important is the careful distribution of weight throughout the ship, aided by strategic placement of cargo and the use of ballast tanks. The materials used in the construction of ships also matter, with buoyant materials like steel, aluminum, fiberglass, and composites proving vital. Lastly, displacement and density come into play, with ships designed to displace their weight in water while maintaining a lower density than the fluid they're in. So, buoyancy isn't just about being light, but also about being smart in design, material, and balance. Remember to like and subscribe for more interesting insights into the world of science.